Hi class. In this video lecture we're going to talk about the method of Frobenius. To remind you that we're interested in solving second-order linear ordinary differential equations with variable coefficients. If these were constant coefficients, we could use the methods we've already discussed to solve them. In particular, we're interested in the possibility that these functions p of x and q of x are actually not smooth functions at some point. In particular, we're interested in understanding the properties of these equations, the solutions of these equations near a regular singular point. For convenience, we'll assume that we're expanding or interested in the behavior around the point x equals 0. For a regular singular point at x equals 0, x times p of x, not p of x itself, but x times p of x is a smooth function around x equals 0 and therefore has a Taylor series expansion. X squared times q of x, not q of x, but x squared times q of x is smooth and has a Taylor series expansion. That means the function p of x can blow up like 1 over x near the origin, and q of x could blow up as much as 1 over x squared. Now, because the coefficients in the equation are singular around the point x equals 0, we expect y to be singular as well. So we don't expect there to be a Taylor series expansion, but as we argued last time, instead we can try something that's very close to a Taylor series expansion. We can assume y of x, or let's try y of x is some power of x, x to the alpha, times an ordinary power series expansion, sum on n from 0 to infinity, a n x to the n. If I bring this x to the alpha inside, that means I'm assuming that the function, the solution y of x, has an expansion of the form sum n going from 0 to infinity, a n x to the n plus alpha, where alpha could in principle be a fraction or an irrational number, even complex potentially. We can try to see if this kind of solution will solve the equation by plugging it into the differential equation and seeing if we can self-consistently solve for these coefficients a sub n. If we take a derivative of y of x and we assume that the series is sufficiently well behaved, if it's uniformly convergent in the jargon, so that we can permute the order of the summation, the differentiation, then y prime of x is just a n plus alpha x to the n plus alpha minus 1, and y double prime of x is sum a n plus alpha minus 1 x to the n plus alpha minus 2. We plug these into the ordinary differential equation. Here's the y double prime term. Here's p of x, where we've plugged in our power series expansion for p of x. Actually, we've plugged in our power series expansion for x p of x and divided by x times y prime. And here is the term involving q of x times y. The sum of this plus this times this plus this times this has to equal 0. We can now, in principle, collect terms of the same power of x to the n plus alpha. And since the right-hand side is 0, its expansion is particularly simple. The coefficients of all powers of x to the n plus alpha have to vanish. So, term by term, the coefficients of different powers of x to the n plus alpha have to vanish. The lowest power of x corresponds to the x to the n plus alpha minus 2, where n equals 0. And the coefficient of that, if we collect all the terms from the previous slide, are a0 times alpha minus 1 from the second derivative term, plus p0 times alpha from the first derivative term, plus q0 equals 0. Now, there are two possibilities in this equation. Since a0 multiplies this expression, either a0 can be 0 or this combination can be 0. But by assumption, a0 can't be 0 because otherwise we could just shift alpha and go to the first non-zero term in the expansion. So we always assume that a0 is not equal to 0, and therefore we have an equation that this extra power alpha has to solve. It has to solve the quadratic equation alpha times alpha minus 1 plus p0 alpha plus q0 has to equal 0. This is called the indicial equation. In general, a quadratic equation like this is going to have two roots, two powers of alpha, and therefore you would expect there are two different solutions of the ordinary differential equation that arise from those two possibilities. And this is a question we'll address in the next lecture on Fuchs' theorem. Let's just work this out in a simple case. Let's take this example equation. If I divide by 36x squared, you'll see that p of x, since there's no dy dx term, p of x is exactly equal to 0, but q of x is this coefficient, 5 minus 9x squared, divided by 36x squared. So q of x is 5 over 36x squared minus a quarter. So the first term in my expansion, p0, is just 0, And the first term in Q0, the coefficient of 1 over x squared, is just 5 over 36. So the initial equation becomes alpha times alpha minus 1 plus p0 times alpha, that's just 0 times alpha, plus q0, which is 5 over 36, which if I simplify is alpha squared minus alpha plus 5 over 36 equals 0, which can be factorized into alpha minus 5/6 times alpha minus a sixth equals 0. So we expect we're going to have two power series solutions that solve this ordinary differential equation, one of the form x to the 1/6 times a power series expansion, with coefficients I've called dn, and another of the form x to the 5/6 times a power series expansion with coefficients I've called an. We now plug this into the equation and we solve to see if we can solve for these unknown coefficients an and dn. Well, since this is a linear equation, I can do this. I can do each of these independently. Let me start with the solution that's proportional x to the 5/6. So let me look for a solution y1 of the form sum an x to the n plus 5/6. One derivative brings down an n plus 5/6 in my series expansion. Two derivatives bring down an n plus 5/6 and an n minus a sixth. If I then plug this into the equation, here's the second derivative term, an times n plus 5/6 times n minus 5/6 x to the n minus 7/6 summed on n. Here's q of x, 5 over 36x squared minus 4 times sum on n x to the n plus 5/6 equals 0. The lowest power of x occurs from the n equals 0 term here, x to the minus 7/6. The n equals 0 term here combined with the 1 over x squared here, which is also an x to the minus 7/6. And those coefficients are a0 times 5/6 minus 1/6, or minus 5/36, and a0 times 5/36. And you see that vanishes identically, so we did solve the initial equation correctly, and we can see that a0 is arbitrary. It corresponds to the arbitrary coefficient which can multiply any solution of a linear differential equation. The next term in this expansion has an x to the minus 1/6 in it, and if I collect all the terms, and this is something you should look at the notes and collect and work out for yourself, if I get this equation for a1, which turns out to be a1 times 60 over 36 equals 0, but the only way that can happen is if a1 equals 0. So I found a0 is arbitrary, but a1 is 0. Now something interesting happens when I look at the next term, x to the 5/6. If I collect all the terms that have x to the 5/6 in them, I have two terms involving a2 and one term involving a0. And when I simplify this, I get an equation that relates a2 to a0. It says a2 is a0 times 3 over 64. So this is a two-step recursion relation. a0 is related to a2. As we'll see in a second, a2 is related to a4 to a6, etc. If you work this out in general, if you look at the term that multiplies x to the n minus 7/6 for any even n, you get this equation. an times this combination involving n is equal to a quarter a sub n minus 2. This expression here is just a special case of that. In principle, we can solve this for as many terms as we like, and so we see the solution y1 of x is of the form x to the 5/6 times a0 times the quantity 1 plus 3 over 64x squared plus something of order x to the 4th plus something of order x to the 6th, etc. You should try this on your own and work it out because you'll have some examples of this in your homework. Similarly, if we try the solution proportional to x to the 1/6, we get an arbitrary coefficient d0. d0 can be anything you want. And then everything is determined by a two-step recursion relation. If the first term were 1, the second term would be 3/32, and the fourth term, etc. The term proportional to x squared would be 3/32. The term proportional to x to the 4th depends on this term, etc. So that concludes our initial discussion of the method of Frobenius and how we use the initial equation and plug back in to actually form the series solution to a problem. Probably the most important thing to remember is this actually constitutes an answer to the question, what is the solution of the differential equation? The solution is given by an infinite series that looks like this. These first few terms give us an accurate representation near x equals 0, but in principle, as long as the series converges, at least in the region that the series converges, this gives us a solution which is valid wherever we're interested in looking for it. So that concludes this lecture on the method of Frobenius. See you later.